In Block 4, we learned the anatomy of a compass and briefly touched on how that works, but we left out an important concept that needs to be understood if you want to become proficient with it, and that's magnetic declination. Welcome back everybody to Block 5, where we'll learn what magnetic declination is, how to adjust for it when necessary, and how to apply that knowledge to correctly orient your map to true north. Before we get into that, let's talk a bit about compass handling techniques. Depending on the type of compass you're using, it may contain a floating needle with an adjustable bezel ring marked in degrees like the Sunto MC2G baseplate, or like many lensatic compasses, it could contain a floating disc with the degrees marked around the outside of the disc and a fixed index line on the bezel above it. These needles or discs must float freely for them to function properly. If you hold your compass like you hold your phone, it probably won't function correctly. What's important is that the compass is level, away from items that may affect its honesty, and where you can clearly see its face. When I'm navigating, I always wear my compass around my neck on a lanyard so that I can easily refer to it when I want to. It hangs just below my sternum so that it's not too close to my face, but also doesn't hang low enough for my belt buckle to affect it. When I want to check my track, I stop, open my compass, and hold it flat in my hand directly against my stomach with the direction of travel pointing straight out in front of me. In this way, my compass and I become a single unit. If I need to adjust left or right, I make those adjustments with my entire body and my compass as a single unit. This helps me to keep the compass flat and floating, and by simply tipping my head, I can easily see the compass and my direction of travel. Let's use our compass now to find the direction to magnetic north. For those of us using the MC2G or any other baseplate compass with a floating needle and an adjustable bezel ring, the first thing I want you to do is make sure your bezel ring is turned so that 0 or north is aligned with the index line, or as Sunto calls it, the bearing index line at the top of your baseplate. Now, using your holding technique, turn yourself until the red north end of the needle is inside of the red orienting arrow, or shed. This is called putting red in the shed. You and your compass are now facing magnetic north. For those of you with the lensatic version, just turn yourself until the letter N or 0 falls under your index line. The best practice for quickly referencing magnetic north is to always align the red north end of the needle with the index line on your base plate, and not necessarily with the N, 0, or orienting arrow on the bezel ring, since it's possible not to notice that it's out of position. Now that you know how to hold a compass, let's get into magnetic declination. You may remember this graphic from the last block of instruction. I used it to explain why a compass points north. Some of you may have noticed that the magnetic poles and the geographic poles are not only opposite one another, but also offset from one another. The geographic poles lie on an axis around which our planet rotates. They are the points through which all meridians or lines of longitude converge. If you were to draw a straight line from any location on Earth to the geographic North Pole, you would have drawn a line of longitude oriented to true north. When you hear the term true north, you should immediately think geographic north, or the North Pole. They are the same thing. True north lines or lines of longitude are constant. They do not change for navigational purposes. We also learned in Block 4 that Earth's magnetic polarity is opposite to its geographic polarity. But by convention, we call the Earth's magnetic south pole magnetic north, because it's the pole that attracts the north end of your compass needle. It's important to understand the science, but it's just as important to use the standard terminology. even though the two can sometimes seem to be at odds with one another. For the rest of this course, when I refer to magnetic north, I'm talking about the magnetic pole in the northern hemisphere that attracts the north end of our compass needles. As of 2025, magnetic north and true north are located around 400 to 500 kilometers away from one another, which means that for most locations on Earth, there will be a difference between where your compass points and true north. This difference is known as magnetic declination. In some locations, as you see here, your compass will point to the right or east of true north. But in others, like this, it will point to the left or west of true north. And there will also be some locations, as you can see here, where your compass needle will line up perfectly with true north. Unlike lines of longitude, the Earth's magnetic field is constantly changing. This is a result of the turbulent oscillations of the molten iron within the Earth's outer core. These shifts cause the magnetic poles to wander over time, around 15 to 40 kilometers per year, and over hundreds of thousands of years, they can lead to complete magnetic pole reversals, where north and south actually flip. The North Magnetic Pole is currently drifting from Canada towards Siberia, as you can see in this illustration. Because the magnetic field is constantly changing, drawing magnetic meridians on maps doesn't make any sense. What you can find drawn on maps are lines of longitude and latitude, as well as grid lines. This is why we have to make conversions. Okay, let's take a knee here to talk a little bit about direction. We're going to cover this in detail in the next block, but I need to throw a few basics at you now to help get us through declination. Direction is simply an angular measurement taken from a known reference such as true north, magnetic north, or grid north. There are other ways to reference it, but for our purposes, these three are what you need to understand. I'll be showing you two tools you can use to measure direction: your compass and also a plotter or plotting tool, protractor if you will. Both of these methods require a line of reference to zero or orient from. It doesn't matter if you're using magnetic north, true north, or grid north, as long as you understand how to convert from one to the other. Depending on the map you're using, you may find lines of longitude, grid lines, or no lines at all, as you see on the Yosemite map. The four edges of the body of a topographic map are known as neat lines. They are normally drawn on specific lines of latitude and longitude, or lat-longs, and they are specified in the corners. So for maps with no lines across the body, these lines become more important. If you trace your finger along one of the neat lines, you will likely find tick marks that you can connect with a straight edge from left to right or top to bottom, if needed. Sometimes the neat lines will have tick marks for lat-longs and others for grid lines. So make sure you're connecting them correctly, grid to grid or lat-long to lat-long. If you don't want to draw lines across your map, there is another way to do it, and I will show that to you when we talk about orienting the map. Okay, back to declination. When we calculate angular directions from a map while using the lines of longitude to orient our compass or plotter, we're orienting to true north and measuring true north azimuths. When we calculate angular directions from a map using the grid lines to orient our compass or plotter, we are orienting to grid north and are measuring grid north azimuths. When we use a compass, we are measuring magnetic azimuths, which are referenced with 0 oriented to magnetic north. These are offset from true azimuths by the true to magnetic declination, or TM angle, at that location. And they're offset from grid azimuths by the grid to magnetic declination, or GM angle. As you learned in Block 1, In the margin of your map, you should be able to find the declination diagram. In many cases, the declination diagram will tell you exactly what you should do when converting from one angular reference to another, but not always. There will be times when we need to convert a magnetic azimuth to either true or grid azimuth that we can put on our map, and other times we may need to convert a true or grid azimuth to a magnetic azimuth that we can follow with our compass. You may be wondering how this is possible since I said that magnetic declination is always changing. Well, that's a good question. Most good topographic maps designed for navigation will not only show you the GM and the TM angle, but they will also show you the amount of annual change. That's important since maps are not being reprinted every year. In block 1, I told you the map print date found in the margin of the map would become important when we discuss declination. Take a look at the print date to determine the age of the map. Then, either subtract or add the amount of annual change for each year since the printing of the map, depending on whether the map shows a positive or negative annual change in declination. That means if your map was printed in 2016 and the amount of annual change is plus 30 minutes or a half of a degree each year, then we would take that 1/2 degree and multiply that by 10 years since the map is 10 years old now, which gives us 5 degrees of change that we need to add to whatever the map shows the declination was in 2016. If the declination was 2 degrees east in 2016, it would now be 2 degrees plus the 5 degrees of change over the last 10 years, which is now 7 degrees east. If the amount of annual change is negative, then you would simply do the math in reverse. Minus 1/2 degree times 10 years is minus 5 degrees. Then take that from the 2 degrees of easterly declination, and we would now have 3 degrees westerly declination. Since the original 2 degrees east declination minus 2 degrees would bring us to 0 declination, and then minus another 3 means we've gone from easterly to westerly declination of 3 degrees. Now let's pretend that we know there's a 10-degree east magnetic declination where we are standing. What does that even mean? It means that the needle of our compass is going to point 10 degrees to the east or to the right of true north. So when we align the north end of the needle with the index line, the direction we're facing is magnetic north, which is actually to the right or east of true north. If we want to face true north, we need to turn a little to the left. Let's do that while holding the compass in position. Start by slowly turning yourself, together with your compass, to the left. What do you see happening? If you're using a baseplate compass, you'll notice that the number of degrees your needle is pointing at is increasing. If you're using a lensatic compass, you'll see that the number of degrees under the index line is increasing as well. But how far should we turn? The declination is 10 degrees, so we turn to the left 10 degrees. Let's make a rule. Whenever we have an easterly declination and we want to convert from a magnetic azimuth to a true azimuth, we add the declination to the magnetic azimuth. So a 0-degree magnetic azimuth plus 10 degrees of east declination gives us a 10-degree true azimuth. If we now point our compass needle to 10 degrees instead of 0 degrees, we will be facing true north, and magnetic north will lie to our right or east. You're correct in assuming that if the magnetic declination is 10 degrees west, meaning magnetic north lies to the left of true north, that we would follow the same process, except this time we subtract the declination. So a 0-degree magnetic azimuth minus 10 degrees gives us 350 degrees. Remember that this rule is for converting from a magnetic azimuth to a true azimuth. It's necessary when taking magnetic azimuths with our compass in the field and plotting them on a map using true north reference lines. We can write the rule as magnetic to true, east add, west subtract. You will also need to convert true north azimuths to magnetic azimuths. Let's take the same scenario as above and say that magnetic declination is 10 degrees east. That means that all true azimuths I get from my map are actually 10 degrees to the left of where my compass would point if I aligned it to that number in the field without converting it. If I measure a 10-degree true azimuth on my map, I need to subtract the 10 degrees of declination to convert it to an azimuth I can use with my compass. If it happens to be west declination, then I would add. It's the opposite of going from magnetic to true. Let's write the rule. True to magnetic, east subtract, west add. And the good thing about these rules is if you're not using the lines of longitude as your reference, but instead you're using the grid lines, then the rules stay the same. The only difference is that instead of using the true to magnetic angle, you use the grid to magnetic angle. The rules would look like this. Magnetic to grid, east add, west subtract. Grid to magnetic, east subtract, west add. Okay, I'm glad we're done with that. I debated whether to even cover these rules with you in this beginner's course, but I think you should at least be aware of this concept, and you can always come back and replay this part of the lesson if you need to. Now, if I'm being honest with you, I have always hated the idea of having to remember these rules in order to make accurate conversions. The chance of getting them backwards or mixed up is high when you're not stressed. In emergency situations, the likelihood of making a mistake is even greater. If you have a nav kit or a notebook or a rucksack that you always take with you when you venture into the wilderness, you should write these rules down so that you don't need to rely on your memory to get them correct. On the straps of my rucksack, I have written magnetic to grid, east add on one side, and grid to magnetic, east subtract on the other. You don't need any more than that, since if you know from magnetic to grid, east add, you can easily remember to do the opposite for west. And it's the same for grid to magnetic, east subtract. You could choose to write magnetic to grid, west subtract, and grid to magnetic, west add. It's up to you. The takeaway should be write something somewhere that you will be sure to have if you need it. Now maybe you understand why I recommend that beginners use a compass that has an adjustable declination setting. The Silva Ranger 2.0 and the Sunto MC2G are two good compasses that both include adjustable declination settings. That means you just need to know what the declination is in the area you will be using your compass. Once this adjustment to the compass has been made, you don't need to think about declination anymore. The compass itself is now calibrated so that when you put red in the shed, your direction of travel arrow will always be pointing towards either true north or grid north, depending on which of these you entered into your compass. This makes all of the map work quick and easy, so let's do that now. The first step is to decide what lines on the map you're going to use to align your compass. If your map has grid lines across the body, then I recommend using the GM angle to set your compass. And then only use the grid lines for angular measurements. Remember, you can find the GM angle in the declination diagram. If only the lines of longitude are drawn across the map, or if it's clean, meaning there are no grid lines or lines of longitude, like our Yosemite map, then use the TM angle. Since our Yosemite map is clean, and I don't want to draw the lines on the map by connecting the tick marks, we will use the TM angle. Let's take a look at our declination diagram and see what the TM angle is. As you can see, the diagram shows that the true to magnetic angle is 17.5 degrees east. If we wanted the GM angle, we would need to add another 1.5 degrees more to that, which would then equal 19 degrees. So we have found what we need. The TM angle is 17.5 degrees. But are we forgetting something? That's right. Magnetic declination is always changing. And this diagram is showing us what the declination was as of the printing of the map. What is the map print date? I see 1958. That means the data is 68 years old. Maybe the annual change is noted. Nope, it's not. So what can we do? We have two good options. The one you choose will be determined by your circumstances. If you have access to internet, then you can simply go to a magnetic declination site such as the one you see here, provided by the National Oceanographic and Atmospheric Association, or NOAA. Just type into your search engine, magnetic declination calculator, and then click the first one that comes up from NOAA here. You can enter the lat-longs if you know them, or type the city, national park, or address of the location into this field, and then click Get Lat-long. After you see the lat-longs populated here in this field, you can check the date also here. It defaults to the current date, but if you want the declination for a date in the past or in the future, you can select that. Click Calculate, and another window will pop up with the information for the location that you entered, and a map excerpt that you can use to make sure you have identified the correct area. As you see, the declination for the 29th of March 2026 in Yosemite National Park is 12 degrees and 12 minutes east. We'll call that 12 degrees. In 1958, it was 17.5 degrees. That means that over the last 68 years, the declination has shifted about 5 degrees closer to true north, or towards the west. The second way to do this is to calculate the declination yourself with your own compass. But for that, you need to know your location on your map, and you need to be able to identify a terrain feature both on the map and visually across the landscape. The further away, the more accurate your calculation will be. Measure the true azimuth from your location to the specified terrain feature on your map. This angle will not have changed over the 68 years since the map was printed. Then, carefully measure the magnetic azimuth to that same object across the landscape. The difference between the two is the current magnetic declination. If the magnetic azimuth is smaller than the true azimuth, then declination is east. If it is greater than the true azimuth, then declination is west. Ideally, as a student of mine, you shouldn't need to perform this calculation, since magnetic declination should be something that you find out as a part of your route planning process before you step foot into the wilderness, when you have the resources to get the information in a more reliable way. Today we'll use the 12-degree east declination that we got online, and we can now adjust our compass accordingly. Okay, to set the magnetic declination, you need to know the amount of declination in degrees and the direction, either east or west, and then you can start. I'm going to show this to you on my Sunto MC2G, but the concept is the same for most baseplate compasses with adjustable declination. On the back side of this compass, you'll find the tiniest brass screw that you've ever seen, and then connected to the lanyard is the tiniest little screwdriver that you've ever seen that goes along with that screw. If you're attempting this procedure on your own and your vision is even the slightest bit less than perfect, you're going to be lucky if you accomplish it with any accuracy at all. Now, I once held the door open for a coat rack, so I had to come up with a workaround for this, which is what you see here. I set my phone on something stable so it hangs over the edge a bit, and I zoom the camera in so I can see what I'm doing. Okay, we need to turn this microscopic screw here until we get to the 12-degree mark of the easterly declination side of the scale. You can see that this side is for westerly declination. We want the easterly side, so we're going to push this black tick mark until it reaches the 12. And I'm going to go ahead and try and do that now while you guys are watching. Hopefully it doesn't take me forever. Whoops, wrong way. Here I'm at the 10. I need to go a little bit further. I'm at the 12 now. After you get it set where you want it to be, you're finished. Okay? Now, all you have to do when you want to use your compass is make absolutely sure that this 0 degree mark on your bezel ring, or where the N is on your bezel ring, is lined up with the bearing index line of your compass. So, like this. Once you have it set like that, then when you lay your compass down, you just need to put red in the shed. That means we just need to put the red needle, north side of the needle, in the red orienting arrow, which is also known as the shed. Once that's done, like this, then your compass and the bearing index line and your direction of travel arrow are pointing to true north, since we have adjusted the compass to accommodate for the declination. Okay, now that our compass has been adjusted for magnetic declination, we are ready to orient our map. When we orient a map, we're simply turning it so that the terrain features on the map align accurately with the actual landscape. This is helpful for two main reasons. First, when you're holding your map oriented in your hand and you're facing your direction of travel, you can simply look down at your map and quickly identify terrain features you should expect to see left and right of your azimuth as you move through the wilderness. While navigating through the woods, it can oftentimes seem like everything looks the same. And once this happens, your confidence begins to make room for doubt. And before you know it, confidence moves out entirely and doubt takes charge. What your confidence needs to kick doubt out and stay in charge in these moments is what I call a warm fuzzy. A warm fuzzy is the feeling you get when your actual experiences along your route match your expectations. That might be as simple as a creek or stream that comes to visit you along your azimuth from the right and then bends away again. Or maybe you see that on the left of your azimuth, there's a deep draw that will greet you around the halfway point. Actually seeing these features along your route where you expect to see them allows your confidence to collect that warm fuzzy and keep doubt outside where it belongs. The second reason why orienting a map is useful is when you want to measure azimuths on a map that has no longitudinal lines or grid lines drawn across its body to line up a compass or protractor on. This we will learn in the next block of instruction when we actually get into measuring direction. So, step 1. Since we adjusted our compass to the TM angle, we need to align it on a line of longitude. And since our map is clean, we'll have to use one of the north-south running neat lines. First, make sure your bezel ring is turned so that north, or 0, is at the bearing index line. Then, align the edge of your compass to a neat line. Turn the map and compass together until red's in the shed. Once you have done that, your map is oriented to true north. Now, the picture you see when you look down at your map should match the picture you actually see when you look up and out into the landscape around you. Okay, we did it. I know that was a lot of information. I'm sure it didn't all sink in. Take some time to practice these steps with your map and compass at home, where you know where you are and where your next meal is coming from. Because trying to remember this when you're lost, cold, tired, and hungry will be much more difficult if you haven't practiced it at all. It's this kind of training that will help you to build the skills you will need to have the confidence when it matters. Follow me now to block 6, where we're going to put all this together and learn how to measure an azimuth on your map that you can follow through the wilderness. I'll see you there.